so today we're going to continue to go over the fundamental theorem of calculus, FTC. But we went over part 1. I'm going to go over some more about part 1 before we get to part 2. So in the Do Now, you were given 4 different problems in where you had to apply part 1 of FTC. So hopefully you noticed when you did the Do Now that A and D had the same exact answers. A and D had the answer of dy over dx equals e to the negative x squared. Okay, so now in this problem it says match the functions in the Do Now that has the given derivative, okay, and the numerical value. So from 1 through 4, okay, you're matching with A through D in the Do Now. So number 1, you're either going to say that it is matching with A or D because that is the derivative. Now, this is saying y of pi is equal to negative 3. So that means that the x value being pi, the answer is negative 3. So take a look at A. It had a y value and an x. And take a look at D. It had a y value, x. And it was a little bit different because the lower limit of integration was different, and we have these values after our integral. So if you remember from our slide that I asked you guys to copy, and it's a property, if this value of x gets replaced, and it's the same as your lower limit of integration, then this whole thing, or that one, would be 0, okay, which is a good thing because then 0 minus 3 would be negative 3. So if pi was plugged in here, this would not be 0, okay, it would be some other value yet to be determined. But if D, choice D, the x was replaced with pi, this is indeed 0, and 0 minus 3 is negative 3. So the y value is negative 3 if x is pi. So the answer for number 1 is D. So I'm actually going to jump over to number 4. Number 4 would be A. And the reason for that is because if I replace the x value with 1, I now get 0 for my integral. And 0 minus negative 3 is negative 3. So my answer here is A. So now you must have noticed that B and C had the same answer in the Do Now. So dy over dx is secant of x. So now in number 2, I cut it off, but it says that y of negative 1 equals 4, whereas number 3 is the same answer of dy over dx, but y of 0 equals 4. So if you look at choice B and C, okay, B looks like this. And if we replace the x with a 0, then this would be 0 plus 4. The answer would be 4. So this refers to number 3. So 3 is B. And if we looked at C, it was this. And if we replaced x with a -1, then this would be 0 plus 4, which is 4, and that would be what we wanted here. Our answer for number 2 is C. So hopefully you can see how the fundamental theorem of calculus, part 1, works. All right, so we're almost off to part 2 of the fundamental theorem of calculus, or FTC. So again, if you don't have the notes, you can always pause your video, make sure you get down all those examples that we went through. We went through 4 different examples. So if you ever see it again and you're like, I don't remember ever doing this, we did it 4 times. Not once, not twice, not even 3 times. We did it 4 times. All right, so when we went over FTC part 1, we talked about an antiderivative, okay? So the general antiderivative, the one that we need to make sure we have written, is capital F of x plus c, okay? So before we were just kind of saying f of x. C could be 0, that is true, if you're wondering. If it is 0, then yeah, it's just f of x. But generally, there is a plus c. You have to make sure that if you're writing an antiderivative, you have the plus c. Okay. So you may have noticed that there were like different, I want to say, derivatives, but they were for different integrals in the do now. So I kind of skipped over the last slide had a very good question, and that was if 3x squared is the derivative, then what is y? And that kind of explains what is being described here, okay? So x cubed is an antiderivative. Many kids say this is what capital F of x is. But x cubed plus 1 is also an answer. Because if we take the derivative of x cubed plus 1, we get 3x squared. X cubed plus 3, okay, is an answer, because if you take the derivative of this, we get 3x squared. So generally speaking, it's anything with x cubed. So it could go on and on and on and on. I'm putting like a triple ellipses there. So that's what I mean by a general antiderivative. Okay? There's more than just one answer that would give you 3x squared as the derivative. Okay? And that's why it's so important that you write f of x plus c, because plus c generalize it, hey, it could be anything. It could indeed be 0, but it could be plus 1, it could be plus 3, it could be minus 3, it could be plus 1,000, it could be minus 1,000,000, and your derivative would still be the same, it would be 3x squared. So when we talk about functions or equations and their derivatives, I like to set up like a table or a chart so we can understand the relationship. So when y is x, y prime would be 1. If y was x plus 1, y prime would be 1. So there's always a like plus c. X squared, y prime would be 2x. Okay, x cubed, y prime would be 3x squared. Again, a constant does not change any of these answers in the table. Okay, so let me get to this slide here. If you're asked to evaluate an integral like this, you must write plus c. Okay, now we're up to part 2. In part 2, a lot of times students think, oh, we don't have to write the plus c. In part 2, it kind of goes away, and I will show you how. So this is the one that students like to do, and we use all the time when we do learn the rules of integration down the road, and we get to find the area under the curve using just rules. So this is becoming like the most popular one, but it's not most important. FTC Part 1 is just as important. All right, so if you didn't copy down FTC Part 2, make sure you do. So as it says, this is a third way to find the area under a curve. So one way is by approximating with Riemann sums. Another way is to do the limit of R ram sub n, which again is still Riemann sum. So we have an approximate, we have an exact value. This will also give you an exact value if we know what x is. Sometimes we write a b there, but it doesn't matter. Okay, so we do capital F, so it's the antiderivative of this, and we plug in our upper limit of integration, and we subtract F of our lower limit of integration into our antiderivative. Well, that's really it. In our antiderivative, it is an f of x plus c. Or an f of a plus c. But that constant is the same. So there's no like subscript c sub 1 or c sub 2. They're different constants. Later on, we'll talk about when they're different. It's still a constant. But in this particular case, they're exactly the same. So if this is, let's say, 4, that is 4. So what happens when we subtract these two, 4 minus 4 becomes 0. So it's not that we just kind of get rid of it, that plus c isn't important. It is. It's very, very important. It's just not needed when you do the subtraction because it will always become 0. Okay, so now that that's all said and done, we have example 1 here, and we're going to do 1, 2, and 3. Okay, so step 1, or first thing we need to find, is determine the antiderivative, okay? And so when we find the antiderivative, then put the plus c, generalize it, okay? So we have capital F of x equals something plus c. Okay, so we didn't get into the rules of integration just yet. That is to find our antiderivative. So for right now, we just have to kind of understand the association between what we know our functions are and our derivatives are. So in this particular case, I wrote down, hey, when y is sine of x, y prime is cosine of x. When y is cosine of x, y prime is negative sine of x. So if we need the antiderivative, we kind of have to work the other way. If our integral was the integral of cosine of x with respect to x, we just simply write sine of x. Unfortunately, that's not the case. It was sine of x. So instead of writing cosine of x, we have to actually write negative cosine of x. That is our antiderivative for positive sine of x. All right? So when you have to an integral, try to reverse this the other way. So the integral of sine of x with respect to x is capital F of x equals negative cosine of x plus c. So, the hard part is over. Number 2 says use FTC part 2. So when we do FTC part 2, now that we have our antiderivative, we're going to apply it. So it's two things that are being subtracted. Negative cosine of pi, it's our upper limit of integration, and negative cosine of 0. Please show the substitution, it's the most powerful thing. And then we evaluate. So we should know that cosine of pi is negative 1, and we should know cosine of 0 is 1. So we have a negative 1 minus a negative 1. This actually becomes 2. Okay, so knowing your trig values are very important. 3, determine integral for the answer. Oh, we actually did that already. If answering an area question, determine the area above and add the area below. The area below would be a positive integral, okay, answer, and the area below would be a negative integral, like answer. We went over that before. So I'm just trying to give a general note there. I'm not sure if it's grammatically correct, but here we go. For sine of x, this is a common function from 0 to pi. This is entirely above our x-axis. So the area under the curve is exactly what we found. It was all positive, okay? Its answer is 2, exactly 2. Okay, you don't need to write the square units, but just write 2, a equals 2, or a equals 2 square units. Okay, let me know if you have any questions. Good luck.